I will begin. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to again bless this work, bless our time together. I just pray that we understand a little bit more about your creation today and that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So let me talk about the problem I omitted. So example 1, because I didn't really need to omit it. It was actually a pretty simple problem. It would have been harmless to leave it in. So let's talk about it. You got a hoop, all right? So basically, think of it like a wagon wheel or something, but the mass is almost entirely on the wheel itself, right? So think of it like a hula hoop, right? But somehow it's got an axle, right? And it's situated such that it can rotate around this axle, right? But the mass of the axle is irrelevant. So we have somehow, however you want to imagine that, all right? Because we're told in the book that it's, pulled with a force F, like so, right? We're told that this wheel, this basically hoop, is pulled with force F along its center, right? And then the question asks you to find the acceleration, right? As well as the force due to friction, given that it rolls without slipping, all right? So rolls without slipping. And let's see here, what else? Radius R, right? Mass M, all right. So one of you guys asked me about this in office hours, and I was happy that they did, because it stumped me. When you asked me about it, I got stuck, because I couldn't figure out how to make progress on the problem, and I talked myself out of something that I shouldn't have. The thing I talked myself out of was that the torque equation is uninteresting, or is interesting, right? It actually is interesting. The torque equation is interesting here. So what are the torques on the wheel? So first of all, the moment of inertia in this context would be just mr squared, right? Because all of the mass is distance r away from where it's rotating, yeah? So we can say that the moment of inertia, right, times alpha should be equal to the net torque. Now what is the net torque, though? See, this is where I tricked myself. I thought that the net torque was 0. See, because the pulling force, does the force which pulls here, does that give you any torque? So this is an interesting problem because it's got a moving axis. And you can still talk about rotational motion if their axis is moving, provided the axis is, like linearly translating. It still makes sense. You can have a moving axis, and you can calculate the torque with respect to a moving axis. You're moving the force with it, all right? But that force is radial, so it gives you no torque, right? But it's rolling without slipping. Where's the friction force? This is actually a really good problem because it involves the concepts we've talked about, but it's not one we've done. So you really, if you could do this problem, that means you have a very good understanding of this material. And if you can't, like me, it means you have a conceptual hole, right? So, or maybe, for me, it's more the issue is you can't ever do physics when you're in a hurry, right? So I was in a hurry because I'd left my laptop in the car, which may or may not have been locked because I didn't get my backpack, and you guys have heard about it. Well, in my calculus, you've heard about it, right? Yeah, I talked about this. So I just got on my bike, went to my office, thought I'm here super early, woohoo, and I feel so light. Oh, because my backpack is in my car. So I went back in between office hours to go get it, but I had a couple people come to office hours for questions, which meant I was getting towards where I wouldn't be back in time for college algebra in time. So I was trying to do this problem in a hurry. It's always a bad idea, right? You're like, well, tests have time limits, so I have no choice. Fair enough. So try to solve more problems before, so that you're conditioned, right? I think that's going to be the direction of the force of friction, right? If the wheel is rolling without slipping, it must be that it's pushing on the road that way in order that it can keep going this way. So the force of friction's got to be, I'm pretty sure, that way, yeah? Just check my intuition on that. If that's the force of friction, does it make sense? That's going to give you a torque, right? What direction is the torque from the force of friction? It's what? I got to do R crossed into F like this. So my axis goes into this. So I'm rolling like this if the friction's like that, which makes sense. We're rolling this way. Okay, so the torque then is that. So what I have then is R times the force of friction, right? On the other hand, that's equal to what? M R squared alpha. So what do I get? But what is alpha, by the way? Rolling without slipping, what's that tell me? It tells me a few different things. One of the things it tells me is that the acceleration is equal to R times alpha, right? So the linear acceleration is related to the angular acceleration in this way if we're rolling without slipping. So that tells me that this alpha is actually A over R. So I've got M R squared A over R is equal to R times the force of friction, which I don't know. And of course the R's, they be canceling, and then you can cancel another one. What do you get? You get MA is equal to the force of friction. Aha! So if we knew the force of friction, we'd be in business here. We'd find that the acceleration is equal to the force of friction divided by the mass. What else do I know here? So not writing this down is what kept me from solving the problem in office hours when one of you asked me about it. I talked myself out of it, even looking at it. What we did look at was Newton's second law, right? Newton's second law here says this. It says the mass times acceleration is equal to the net force, right? Now I'm just talking about the magnitude here. Pop, pop. So, did that register? Dang it. I tried. Should I explain the joke? All right. In Community, there's this character called Magnitude. His characteristic phrase is pop, pop. I clearly said the word magnitude, and I inappropriately said the phrase pop, pop in the middle of the lecture. This should have been sufficient. The joke stands. The joke was valid. I have proved the joke. Sorry.
So you have watched it.
I love is it Chang? Like
Professor Chang.
the guy, what's his name? I can't remember the actor's name, but that character he plays, that Chang character, it's beautiful. And that little girl, he starts having like the devotees, like the religious followers, who start praising him like the sun. It's beautiful. There's moments in that show, or yeah, I like that show. Right up until it got pretty weak though. After it got too self-indulgent after Donald Glover left. It just kind of got So, yeah. And I really dislike what's his face there, the old one. Yeah, that one. So liking the show despite his presence on it is saying something. But I don't know, it's an interesting show. I've overheard students of your generation saying that The Office isn't funny.
Whoa.
But you guys said The Office wasn't funny. It was funny, right?
Yeah.
It's funny?
Yeah.
Okay, just checking. I said yes. So maybe The Office is more intelligent than I realized. Maybe I'm just surveying the wrong classes.
Yeah, Michael Scott's super smart.
Is that it?
Oh, yeah.
Yeah, I don't know. I do have a student that's been watching Seinfeld to try to understand white culture better. I think it kind of, I was like, that would be sort of like me watching a show about the Jamaican like about Jamaicans to understand black people better. It's like, it's a very specific subculture of the space of all people, right? Like, it doesn't make sense. If you want to understand affluent, white Jewish people who happen to live in New York City in the 1990s, it's very relevant. But outside that context, maybe not so much, right? I don't know. But I'm fascinated by this idea of watching a TV show to try to understand another segment of the population's culture. I mean, there is something to it, I think if you want to understand white culture, maybe just like read a lot of the Babylon Bee. Babylon Bee is very, very white, right?
Do you recommend it?
Yeah. I am, after all, white, so yes.
I didn't notice. So.
Yeah. So you don't see color? That's right. That's good. Let's see here. So, what was the net force? I guess I should get back to the physics. We're getting close to the place where I have to edit this out. So, and I hate editing. So, what's the net force? There's two forces, right? Well, there's three, right? Well, the other force would be there's like force of gravity, right? And there's also the normal force that pushes back up. Those are equal opposite, they cancel out. Right, so those vertical forces we don't care about. So we can just look at the magnitude, pop, pop, and I don't know if it's valid now that I've explained it. So F minus the force of friction. No, there's several characters in that show I really dislike. Yeah, I still like the show. That's saying something. I think if you can watch a show that you dislike all of the characters, like dislike all of them, but you still like the show, that's actually a very good show. You know what I mean? Because you like it for the story, not for, a particular person or something. But there are a few things like that. But okay, let's see here. My God, what have I got? So then, see this? Look at this. We've got this, and we've got that. What happens if you add these? We get 2ma is equal to F. See the force of frictions, they be canceling? And so this gives us that the acceleration is equal to F over 2m. Now, if I had not omitted this problem from the homework, I assume that you all would have given me the correct answer, because I posted a PDF which has the statement of the problem, and at the end of that PDF I have the answers from the back of the book. So the answer was given to you in that PDF at the end of it, if you hadn't noticed. I probably should have told you that earlier this semester. But you've noticed, right? You guys are going to find an answer. So let's see here. So A is F over 2m. And then now that I know that, I can go back over here. What's my force of friction then? Force of friction, ma, right? So m times F over 2m, which is just what? F over 2. So that's why the force of friction was half of the force that's pulling the wheel, and the acceleration is F over 2m. Does that make sense? Yeah.
On the line where it says MA is F equals F minus force of friction, how do you know you can subtract those reasonably without considering two dimensions?
Oh, it's just what I said in words. The vertical forces cancel.
Maybe they're applied at two different locations dimensionally, vertically, I guess. So one's applied here, and one's the other.
Well, let's see here. So the question is, where does the force of gravity applied? I think we can all agree that the normal force is applied here, right? That's the normal force. Where's the force of gravity applied? Well, it's an extended object, right? So if you want me to get more truthful about it, it's applied at an infinity of locations, and we'd have to integrate. There's like one here, 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 one here. The difference between the what? The force of friction and, oh, these two? But they're both horizontal. The disparity in whether at point of application, that's addressed by the torque equation. See, to find the net force on a system, we just have to calculate the sum of the external forces on the system. The actual point of application of the force doesn't have to be the same at different points in the extended object. So like here, yeah, I'm applying the force of friction at the bottom of the wheel, and we're applying the force that pulls the wheel in the middle, sure. But we think of the system, the wheel, as the object, the collective object. And so the net force, I just take the sum of all external forces on it. And there are two external forces which are not pictured in that picture, right? The normal force and the force of gravity, but those are vertical and they cancel. So that's why I could just look horizontal. But there is something to think about there. You're right. If you have an extended object like a refrigerator, right? And everything being equal, you take two forces and apply them at different points on the refrigerator, different things will happen, right? Like if the force is sufficiently large, one will make the refrigerator tip over one way or the other way, or make it just slide. I mean, these things matter if you're a mover. But the motion of the object, in this case my refrigerator, around its center of mass, that is described by the torque equation. So it's the combination of the Newton's second law and the torque equation together, the rotational Newton's second law, that describe how the motion of an extended object goes. And there are additional examples and discussion in the chapter in the book on equilibrium, which we don't cover. So we just touch on these things. We don't delve too deeply into them. If you're an engineer, you should have a whole course called statics. It should be all about this, wall to wall pretty much, I believe. I haven't had the course, am I right? Oh, I'm asking you guys. You haven't had it yet. This is a prerequisite, right? Yeah. You taken it before? Is it about balance and forces and torques? Okay. Woohoo. So, well, now that you know what the course is about, I guess you can skip it, right? Yeah. Yeah. Anyway, so actually, I think this is actually a really nice example. So. Oh, I was going to put it on test, but now that you've asked about it.
I think you still can, for sure.
See, I don't know. It was more certain before you said that, though. So.
Guys,
It's kind of like we have to think about, there's two cups. One has poison,
All different poisons in one. You guys can go on. I'm very sorry.
You have to weigh different things, like a land war in Asia, things like this, Let's see here. Example 2. Was that too obscure a reference? No, okay. So you guys have watched The Princess Bride, but you don't know what UHF is. This is weird to me. What? It's a what movie? Huh? I didn't hear. Oh, Fire Swamp. Yes. Okay. Oh, we're making additional Princess Bride references. Okay. Very good. Very good. I'll allow it. Okay. So, any questions about anything before I go on? All right. So, Sam was starting to talk about issues of orbital mechanics, and I don't think I've given a full explanation for that, but I just want to ask a much more boring question, which is, you're on Earth, ignoring everything else, right? Here's Mr. Top Hat, right? And takes a cat. All right. And takes the cat and he kicks it very, very hard because Mr. Top Hat hates cats deeply. Am I Mr. Top Hat? I don't much care for Lincoln, so no. Let's see here. So, let's see here, V. So suppose that he gives Mr. Top Hat an initial speed of v naught, right? So he kicks the cat directly upward, all right? Now we're going to do things like ignore the moon, ignore the stars, ignore the sun, ignore the atmosphere, ignore the fact that if you did kick a cat hard enough to give it this velocity, it would explode in some sort of mist. Sorry, is that too itchy, scratchy? No? Okay. Well, it's true. Come on. You know, there's a guy on YouTube that he puts like he puts a no, I don't think it's a pneumatic press channel. He has it. No, I don't think he's ever done any animals with the press.
I was really concerned more for you than for him, to be honest.
I feel like if you put a cat, I feel like that would get you banned on YouTube. I don't know. I mean, that might be over the line. I don't know. There are hundreds of those. There's hundreds of those frog eating a bug videos that I showed you guys the other day in calculus too, for the calculus, of course. And but he actually, I saw another video. He was putting an orange into like a cylinder and then crushing it with the pneumatic crusher thing, and he was making the orange squirt out like a little, like millimeter size hole, like pulp and all. So I mean, anyway, I should show you. No, it's okay. Maybe some other day. I'll try to find a link and send you guys a link after class. But well, the thing is, whenever I look on YouTube with this stupid machine, it's full of ads. But anyway, so my question is just this: if you're at the radius of the Earth and we're ignoring air friction, all that stuff, how high up does the cat go? All right, so how high does the cat go? How high does cat fly? So we're starting him out at the radius of the Earth. I want to know what altitude. All right. Now this is going to have cases. The answer is not going to be one number. The answer is going to depend on what v naught is. All right. So how do you solve this problem? What's the principle? What's conserved? Energy, right. So we use conservation of energy. And what's the energy? Energy at the start is equal to energy at the end. So what we're talking about here is 1/2 m v naught squared plus what? Well, I should say minus what? Minus m, let's see here, how does it go? Big G, mass of the Earth, divided by radius of the Earth, plus the altitude. If I remember right. Do I remember? I think we worked that out last time, isn't that right? It was GMM over R, and it was minus, isn't that right? Then I graphed that last time. I said the potential energy due to gravity was minus G little mass, big mass divided by R. And I said that, you know, the graph of it looks something like this, right? Remember that? So I'm using that formula here, but with R equal to, you know, radius of the Earth plus altitude, okay? And that's equal to the final energy, right? Which is what? What would if it does turn around, what's the final kinetic energy at the highest point? 0, right? This is one of the first things we did in here, right? Oh man, turnaround point. It has one job, you know? Ay, ay, ay. So 1/2 m times 0 squared, right? Minus mg, mass of the Earth, divided by radius of the Earth, plus h. Now, did I need the h over in the other one? What was h here? I should have just put that to 0, right? Because to start with, you're at altitude 0 when you kick the cat, right? I can tell you that the cat is evil, but that's redundant information. Let's see here. So, question, what's the max height then? We could solve for h, right? Let's do it. So we have, oh, by the way, what should we get rid of? We can get rid of the mass of the cat, right? So it's everywhere. So it's nowhere. And let's multiply. No, we don't need to multiply. All right, so what I have is 1/2 v naught squared plus g, mass of the Earth. Oh, man. My bad. Minus g, mass of the Earth, divided by the radius of the Earth. And that's equal to minus g, mass of the Earth, divided by the radius of the Earth, plus h. I'm trying to solve for h. So what should I do? I should divide. Fine. Algebra, right? Okay, so I get g times the mass of the Earth divided by 1/2 v naught squared minus g, mass of the Earth, divided by the radius of the Earth, is equal to the radius of the Earth plus the altitude, the max altitude, right? And so we can solve for h. What do we get? I get h is equal to, whoa, dude. G times the mass of the Earth divided by 1/2 v naught squared minus, if I made a mistake somewhere, let me know about it.
I think you're
Missing
missing a minus.
a minus?
In front of the big, yeah. In front of, yeah. Negative g.
Oh, so let me make my correction in red. I agree. So I should put it here, and then here again, right? So let me just clean this. Let me rewrite this equation just a little bit. So what I have here is g, mass of the Earth, divided by 1/2 v naught squared. My bad. I'm trying to put the minus in. So g, mass of the Earth. I'm going to multiply the top and the bottom by the radius of the Earth. So I get gm minus 1/2 v naught squared times the radius of the Earth minus the radius of the Earth. So we can clean that up a little bit. This is g times the mass of the Earth divided by g times the mass of the Earth minus 1/2 v naught squared times the radius of the Earth minus 1 times the radius of the Earth. So if we actually had some numbers, we could put it in there and figure out actually what the max height was, right? Of course, we remember the radius. You guys remember the mass of the Earth from before, right? 5.924 times 10 to the 24 kilograms. Is that right? Or did I remember the 7 wrong? It's about that. What's the radius of the Earth? Approximately, what was it? 6.38 times 10 to the, was it 7th? I can't remember. 6th? 6 meters? 6.38 million meters. All right. Interesting. What were the units on big G? What's G equal to? 6.67 is it? Times 10 to the minus 11. What are the units? 1 over kilograms? We worked this out. I don't remember it. You guys help me out? What are the units on big G? I'll work it out, I guess, if you guys don't tell me. So the units on big G are
Newton meters squared over kilograms squared?
Newton meters squared over kilograms squared.
Yeah.
So that works out to 1 over kilogram meters cubed times 1 over seconds squared, right? I'm just looking at this. Is this dimensionally consistent? Check this out. So I've got G times the mass. The kilograms cancel, right? And that leaves me with a meters cubed over seconds squared. How's this go? I've got a velocity squared. That's meters squared over seconds squared times a meter. So that's a meter cubed over. So it's dimensionally consistent. When I do a lot of algebra, I try to check at the end and make sure that my answer is dimensionally reasonable, because it's easy to make a mistake in the algebra, right? Especially when you don't have people watching you making sign errors and stuff like that. Okay, so question, is this a reasonable derivation of the altitude? Why or not? I mean, it could be. Let's plug in some numbers. So you guys tell me, what's G times the mass of the Earth equal to? So I get GME for me works out to about 3.95 times 10 to the 14th. And that would have units meters cubed over seconds squared, yeah? And, excuse me, so we've got, 3.95 times 10 to the 14th divided by 3.95 times 10 to the 14th minus, what's 1/2 of the radius of the Earth? So 3.19 times 10 to the 6th meters times what? Times V naught squared. All times the radius of the Earth, right? Where the radius of the Earth was 6.38 times 10 to the 6th meters. All right. Yep.
But we still need to subtract 1 on the inside.
Ah! There we go. It's hideous, but there it is. Oh, did the camera move over here? Okay, that's cool. So my question again, does this make sense? Let's try putting in, V equals to, I don't know, 100 meters per second. What happens? If I was smart, I would probably use like Wolfram Alpha and put this stuff in so we could change the number real easy without using our stupid calculator like I'm currently doing. I said 100 meters per second, right? So I'll work that out. Oh gosh, it's really, really close to 1. If you round off things even a little bit here, you're going to be all kinds of wrong. I don't entirely trust the calculation I'm doing right now because of the numerical issues.
5.15.
Yeah, I got 515. I get 515.3 meters. Let's try that out. How we would have done this before? We would have done what? 1/2 mv squared, v naught squared equals to what? mgh. H would have been equal to what? V naught squared divided by 2g, right? So what's 100 meters per second squared divided by 2 times 9.8? How does that square up against what we're doing right now? I bet we're going to get something that's, it should be really, really close. Why is that? Now I get 510.2 if I use 9.8. But keep in mind that every time we use 9.8, maybe we should be using 9.79 or whatever. I forget, 9.8 is an approximation, right? When you actually crunch the numbers of the g mass of the Earth divided by the radius of the Earth squared, it didn't work out to quite 9.8. It was something else, right? I don't remember that something else, but that something else is what I would expect would be more accurate but as you can see, ballpark, right? Up to the slop in using 9.8 versus 9.793 or whatever it was. This makes sense because MGH is a very good approximation to the potential energy as long as we're not very far away from the surface of the Earth. And that would be the case for this example. 100 meters per second. What was the escape velocity we calculated last time? What was it? 11,100, 11,200 meters per second, right? So about 11.2 kilometers per second, something like that, was escape velocity. Okay. Instead of doing 100 meters per second, how high should this go if you go, I don't know, V naught's 12 kilometers per second? What's the max height in this situation? Yep. It's right. It just escapes. My question doesn't make sense. In other words, there does not exist a altitude high enough to solve the equation that we wrote down. This whole thing was based on the fundamental premise that if you go far enough out, right, this quantity here can be made equal to what? This quantity over here. What is this? This is negative, right? This is a negative number. So if over here, if this is positive, you can't solve that equation. So all that you have to do is to have V naught sufficiently large that your total energy is positive. If the total energy is positive, that means in terms of the energy diagram, you're up here. Which means, yeah, there's no max radius to which you go. You escape, as Justin said. How this translates to your test or final exam is if you don't think about this and you try to do the math, you'll end up with like imaginary numbers if you're not careful. These things will happen. I don't quite see how that happens in the current calculation, but it does. If you ask the question in the right way, you end up with like imaginary numbers and junk. I've seen it happen before. But it's just simply this. If this is positive, there's no way you can find H sufficiently large to make this, this is always negative. It just is. So, unless you could have like a negative H, right? But that wouldn't be physically reasonable, right? What would negative altitude mean? I I guess that could mean you're underground, right? So I'm a little bit wrong about that, but definitely if your h is what? If your h is less than the radius of the Earth, like negative radius of the Earth is the lowest altitude possible, right? And even that, I don't know, it's kind of straining, a little bit straining credibility, like most of my examples, right? So, okay, let's go on. So when do you use MGH? When do you use GMM over R? How do you know which one to use? As a good rule of thumb, if you're going to find an H, which is like, let's say more than 100, more than about 100 miles or so, you probably should be using the other formula as a sort of a rough guide, because the error goes something, the error is like linear with H, and I think, if I remember right, the, oh man, where's my juice? I thought I didn't have any juice there for a second. So suppose you have a planet. Anyway, what I was trying to say there was just this. You want to use the more complicated GMM over R formula if you're dealing with large distances. If you're close to the surface of the Earth, and your speeds are not larger than, let's say, 10,000 kilometers per hour. Per second. 11 kilometers per second. I'll get it right eventually. Units matter, right? If you have a speed that's larger than, 10,000 meters per second, then probably you should be using the other formula, because you're getting close to the escape velocity. Probably it's relevant. Unless, of course, you're shooting your gun into a, pile of dirt or something, so the escape isn't going to be relevant. But all right, enough about that. Suppose we have a mass, a planet, all right? And you have a pair of moons, all right? And so we've got a moon here, and one down here, all right? And they're symmetrically situated. So radius R here. And let's suppose that we also have radius R to here. I probably haven't managed that. So we've got the mass of the moons, let's say, is little m. Suppose the moons are equal mass, all right? And you've got mass big M for your planet in the middle. All right? So then what happens if it's rotating? I'll tell you what, let's take the mass in the middle out. Make it simpler. Just a pair of moons. There are things like this called binary stars, a pair of stars that are orbiting each other like this. We've observed these things. They're actually pretty neat because of the way they're orbiting, if they're orbiting such that they're like covering up one or the other as they orbit towards you, if they do like that, then the intensity of them varies. So you can see how fast they're orbiting each other by just looking at the giant blinking, like very distant blinking light, basically. So my question to you is, if this is the situation, right? You got two moons, each mass m, identical, and they're orbiting each other like this. What can you say about it? How is the radius related to the mass? Can you guys tell me how I would analyze such a problem? What should I do? Where would I start to try to understand the physics here? Why are they orbiting each other? What's making them orbit? What makes them go in a circle? If they're going, centripetal velocity is a good answer. That's part of it. So we know that we've got to have mv squared over r, right? What is making that happen? Why is it doing? Why is that happening? Gravity. Where's the gravity coming from? Each other. It's not from itself, right? So let's suppose that we're talking about the upper moon, right? So that it's got a net acceleration like this, right? The acceleration centripetal point, that's its magnitude. Where's that coming from? That is coming from the force of gravity of the other moon pulling on it, right? So what's the force of gravity of the second moon on the first? How far are they? 2r, right? So the force of gravity here, it should be g, mass of the moon, divided by twice the radius squared, right? And that's it. This is the equation which governs the motion of two moons orbiting each other. And so you can do other things. We can figure out that v is actually what? It's, of course the m's, you can cancel one of the m's and you got what? V is equal to g times the mass, g over 4r squared. So I can cancel m, I can cancel an r, and I just get gm over 4r, right? Take the square root. That's the formula for the speed in terms of the radius, right? What's its period? So the velocity is also equal to what? 2 pi r over the period, right? You can tell that the speed is constant, right? Because there's symmetry here. There's no point that distinguishes one part of the orbit from another. There's this symmetry of the problem, so we can expect the speed is constant. And so we can figure this out, right? This would be, so I've got gm over 4r is equal to 4 pi squared r squared over t squared, which give me what? The period squared is equal to 4 pi squared, good grief, 16 pi squared, 16 pi squared r cubed divided by apparently gm, if I haven't made an algebra mistake. So there's the relation of the orbital, the square of the orbital period to the cube of the radius. So this is kind of sort of Kepler's law, right? This is the analog of Kepler's law for this problem. Do you guys know the other Kepler? Kepler had 3 laws, right? What were they? Kepler's first law, second law, third law. Did you guys ever learn it in your science class? Nobody? Oh, no, I thought there was a hand raised in the back there for a second.
All planets move in elliptical orbits with the sun on one focus. A line that connects a planet to the sun's
So, number 1, planets move in elliptical orbits with the sun as a focus. Number 2, a planet covers the same area of space in the same amount of time no matter where it is in its orbit. And number 3, the planet's orbital period is proportional to the size of its orbit. That's not true. Just a second here. That's not quite true. There's a square and a cube involved. Yeah. If you want the truth, go to Wikipedia. So, in Wikipedia, number 3, they write it this way: the square of the planet's orbital period is proportional to the cube of the length of the semi-major of its axis of its orbit. So this is analogous to Kepler's 3rd law. Let me talk about Kepler's, well, maybe next time, I guess. The thing I haven't talked about yet, and we should talk about angular momentum for gravity. It's interesting. It's a neat calculation to see there. And that that other one is essentially Kepler's other law. The conservation of angular momentum is Kepler's other law. So anyway, maybe next time. Thanks, guys.